Let's do it, shall we? Hey folks, welcome back to the shrine. The shrine of the hand-me-downs of the industry. Tonight we're gonna be talking about lifters, or tappets as they are also called, that are being used for internal combustion engines. Just need to clean this up a little bit, make some room for the stuff what is coming. There you go. Tidy up, nice and clean. So what is a tappet? Well, a tappet is a device or assembly in an engine that will change the rotary motion into an alternating motion. So you got a cam, the cam is turning. As the cam passes by, it will go by the tappet or the lifter, and it will lift it up. Well, this one, you can see it's falling apart. It still has these rollers in it, or needles. Some people call it needles. This is from a Harley. It's a Sportster 883, and you can see it's a pretty elaborate piece of machinery. Right here, these surfaces have sort of a mirror finish. There's no surface roughness that can be felt on them, so this is most likely machined, hardened, and then these surfaces are ground and polished. And what you can see here is these are rough cut machine surfaces. So what I did is I took this assembly apart and I created a cross section. I built a 3D model, and so here's a cross section. So this guy down here is the roller, okay, and then this is the body itself. This is a scaled model. It's 1:3 maybe, and in the inside we have an additional piston. Let me zoom in on it. Probably helps. So inside we have a piston, okay. There's a couple springs that are not shown on the model, but down here there's a preload spring, and you can see there's a cavity here, there's a hole, there's a cap on it, some sort of a valve, and if you look carefully on the side of the tappet right here, there's a hole. And so what they do is this tappet is moving in some kind of bore, and in the bore they introduce oil, and so that oil from the galleries will get into this crevice, and from there into this hole, and then from that hole inside the tappet it's gonna get to this bottom side of the piston, and that oil pressure is gonna push the piston up. And so at the end of the piston there's a saddle here, and the saddle has the hemispherical cutout, and that's where the push rod sits. There's a circlip up here on the top, and that circlip basically is holding everything together so it wouldn't rattle apart. And this tappet assembly is fairly large. For my engine that I'm working on, I need about half of this size. So why do they go to this length to pack all these parts inside? These are actually real precision parts. When you take it apart and you try to move these surfaces relative to each other, you can feel a suction because the fit here, the tolerances are so fine. So they do it in order to eliminate valve lash. And so what they do is, when this is pressurized, it's moving up and down, and there's a constant pressure here, and as the parts expand and contract as the engine cools and heats up, you're going to end up with valve lash. And so this is supposed to compensate for the valve lash. I basically bought this because I wanted to look into it and understand how it's done. And one of the interesting things I found is about this pin. So this is the pin that holds the roller, okay, and there's the needles in between. So the roller rides on the needles, and the needles are tightly packed. So as you can see on this picture here, there is no cage or separator within the assembly. So the needles basically touch each other, or there's a nominal gap, some kind of small gap between them. So what I did here is I had to take this apart, and I was initially thinking that there's a press fit between the bore and the pin. And when I took it apart and I looked at it carefully, I can see that the ends of the pin are flared. So you can see that this end is flared and this end is also flared. You can also see that I was pushing it from the left side out to the right, because this flare is kind of straightened out. So when I was pressing it through, it kind of got rid of that flare. Now, why is this important? Well, remember that this is an engine component, and as an engine component, it marches up and down rapidly. So if your engine, let's say, running 5,000 RPM, your camshaft is running 2,500 RPM. So in 1 minute, you're going to have the cam passing by 2,500 times. Okay? So that's rather fast and rapid. And so you don't want these things to fall apart, because it will most likely lead to a catastrophic failure on the engine. And so as a designer, you have multiple choices when you want to retain this pin within the body of the lifter. And so some of the options might be to press fit. So in that case, you would make the bore smaller than the pin, and you would cool the pin down or heat up the tappet and press them together. Or you would just simply press them together at room temperature. Now, this option is probably not a nice way, because when you would be pressing it in, if it's a stepless, smooth pin, then during the press fit operation, this bore would be riding on the surface, which is a real nice and smooth and polished surface made for the needles. And most likely this surface would be damaged during the press fit operation. So a press fit is out of question. The next item would be to cut threads on it and have a male and female thread. You would have the pin, basically, you would have threads on it, you would put a knot on the end. That's also not a good idea, because that would be a stress concentrator, and these parts are designed really at the limit, so there isn't much extra strength designed in them. And if you have a stress concentrator, because it's a high cycle environment, you would probably fatigue it out. And so what this designer came up with is basically they flare the ends. So the pin and the bore has a slip fit when they initially put together, and then they come in with a press or some kind of tool. They're going to press the end, which is going to flare the ends out, and it will create an interlocking type connection. So remember, we want to lock the pin in the bore. So if we are creating a press fit, you're going to have some kind of radial force in the press fit. You also have some kind of coefficient of friction, and that's all that it's holding it back from falling apart. Now, on the other side, if you create an interlocking type, that interlock is a lot stronger lock for a component or an assembly like this. So what I did is I modeled this up, and then I realized that it's not exactly the right size of what I need. So I started looking for similar applications that I might be able to use parts from. And before this, I was trying to contact suppliers from China and from all over the world who make bearings or assemble bearings to maybe get me parts. And I created a drawing, sent the drawing out. I probably sent it to 100 places, maybe 150, and barely got any response. And from the responses I got, nobody was able to provide me the bearing I was after. And so I, a little bit like Bruce Lee, changed tactics, and I started to look what's out there in the market I can buy readily that somebody already makes that would fit my needs. And the idea was that later I tracked down the manufacturer. So here's what I found on the market. So here's an assembly. This is from a Hyundai Elantra or Santa Fe, and 16 valve CRDI. This is from AliExpress, and you can see that this is not a lifter, but this is a rocker arm. And so the way it works is there is a roller here, similar in construction, and you have some kind of valve or standoff that this is riding on, and then you have a camshaft, and the camshaft is pushing on a roller, and then this end is pushing on a valve. And I looked at this part, okay, disassembled it, and when I was disassembling these parts, I was measuring the press out force just to have a ballpark of what I should be designing against. And here's the pin. Okay, so this is Hyundai Elantra. This is designed in South Korea. It's a fairly recent car, so you would think that there will be parts available for this. So you can see that on this side it is flared, and on this side the flaring is partially gone because that's how I pressed it out. But again, the idea is that this is flared. Another thing that's interesting, that there's a groove here at the end, and you can imagine that the way they flared this part is they came in with a tool and they pressed from either side, and that tool penetrated and displaced some of the material, and that's what became the flaring. So you can see that flaring is nice and round and concentric, and it is present on both sides. The next one I found is a Chinese manufacturer. This is Whale SMD for a Great Wall, and this is also from AliExpress. All these parts cost in the range of $5–10 bucks, but here is a rocker arm. Okay, the pin or the roller sits right there, and then here's the pin. Now, a couple of interesting things about this. At first sight, you know, this looks like aluminum or magnesium. It's most likely aluminum. I think there were some markings on it. The second thing is that it does not have needles. So this roller rolls directly on this pin. So it's most likely that the application load is not that high. The third interesting thing is that it has these center bores. which on the other ones we never seen those center bores. So every time you add the feature on these parts, it will make it more expensive. So these parts, the ones that don't have the center holes, they are probably just free ground on a grinding machine. And again, you can see on this one that the ends are flared on both sides. You know, this side has more flare because this is the side that I pressed out. And also you can see that there's a groove, which is not a full groove. It's concentric, so it's nicely done. So it looks like there's some kind of precise manufacturing process was done for this one. I cannot put this in a bore anymore because, you know, when I pressed it out, this flaring acted as a spring when it was going through this roller. One more interesting thing about it is that this is a perfect fit into that bore. So when it's riding, it's a really nice fit. And that mirror inside, that mirror polish inside is just amazing. I can think that you know, this surface might have some kind of surface treatment, some kind of special hardening surface treatment. So this was the whale. The next one I have is for a Ford Mustang. It's a Ford Mustang F-150 racing, 4.6 liters. This is also from AliExpress. And here is the assembly. So what I did here is I took it apart and I basically, you know, pressed it out. And then once I pressed it out, I turned a chamfer on this guy, on this pin. And that is a really important clue, and I'm going to talk about that later. But after I turned the chamfer, obviously I got rid of the flare on the end, but you can see that this slides in easily to the bore where it belonged before. So again, this is a rocker arm for the engine. You got some kind of stud. This guy is riding on a stud. You got the camshaft right here, and then this end is pressing on a valve. So the last one I want to show is a rocker arm, and I bought these. They came as a pair. This is M150GY, and they also call it Racer 150. So all these parts came as a kit. There's some O-rings in it, and there are the needles. But we are interested about this guy right here. So this would be exactly the size that I'm looking for. It is 17 millimeters, and the thickness is 6.5 millimeters, and then the roller is hollow, and it's around 8.3 millimeters in size. So the same thing applies to this one. Okay, so we got the ends flared on both sides, and you can see when I pressed it out, it actually damaged this surface here. So there's some nicks and marks on that surface. So that's what the designers wanted to avoid, because once we have those nicks and those marks, that is actually the hardened surface where the rollers are rolling, and no matter how much oil you're going to dispense there, it is going to wear out in a short time. And I have actually one more of these assemblies, and it's this one here. This is a Harley Davidson, and it's a Evo chopper, Harley Davidson Evo chopper, and it's a repair kit. Now the other problem with these is whenever these components fail, for whatever reason they would fail, they're not going to take these apart. They're just going to take an assembly and swap out the assembly. Because, you know, buying the bearing might be $5 and buying the whole assembly is $10. So people would rather go and just take the whole assembly and replace it. But on all the Harleys, this is what they sell. And you can right away see that big difference. So what we have here is we have a roller, and there are the needles, and you can see inside there is a bushing. So the bushing and the roller is most likely true hardened. So these surfaces where the pressure is exerted either from the cam or from the rollers, those are hardened surfaces. And so they supply this pin. And you can see the pin has two counterbores on both ends. And the pin is actually soft. I run it with a file, and the file was cutting it. And so the pin fits right into this bore. So when you assemble it, what you do is you just take a pin and you press, you know, some kind of staking device or something with a 90-degree cone angle, and you press the ends, and that will flare it. And the pin, you know, still acts as a shaft, so it will roll on it. But where the roller is actually rolling, it's a hardened surface. So the pin is soft, but these surfaces are hard. So that's a big difference between these. Now, some of you might ask, you know, what's a big deal about it? Why can I make something like this in a home machine shop? Well, one of the problems is that these are high precision parts. And when I talk about high precision, I talk about the surface roughness. You know, it's not only a ground, it's a machine, a ground, and it's a polished surface. And they are also heat treated. And the diameter and the cylindricity is just outstanding. I mean, bearing manufacturers can't really do nothing except round parts. The only thing bearing manufacturers know how to do is round parts, but they just elevated the level to perfection. And the way these pins work, the center section is hardened. That's where the rollers or the pins are rolling. And then the edges have to be soft, because if the entire pin would be hardened and you come in with a staking tool, it would break the staking tool, or you would get only a couple parts made with a staking tool. And when you're doing an assembly, you know, a mass production, you want that staking tool to last, you know, 1,000 parts or 5,000 parts or 10,000 parts. So what they do is the edges are soft and then the center is hardened. And that was my idea. So in order to double check that, I mounted one of these parts here. So what we have is this outside roller and then the pin. So from one of these, I cut it in half and I created a mount. And once it's mounted, then we can handle it a lot easier, and then we can also do polishing on it. So this is half the roller, and then this is half the pin. So the other benefit of having a hollow pin is its less mass, right? So when we're designing something that moves fast, we want to minimize the mass, because then the inertial forces and the loads will be lower. And so these are the mounts. Okay, so it's just the part that I shown encased in plastic, so it's easier to handle. And also what we can do is polish this first with some kind of emery paper, and then come back and use polishing compounds, and then we can measure hardness on it. And so what I did, maybe you can see a line. There's a line on this side, and you can see the little points, the little divots. So that's where the hardness tester went in and tested the hardness. And the hardness tester confirmed that the edges here, about 2, maybe 3 millimeters from the edge, are soft. They are about Rockwell 20, and then the hardness goes up, this entire cross section is through hardened, and the hardness in the center section is around Rockwell 62, 63, and then the other edge is soft again. And the same thing applies here. If we look at the roller, I was looking at the roller and going in the radial direction, so you can see this line across here. That's where the hardness was measured from the inside to the outside diameter, and that also confirmed that this entire section is true hardened, and the hardness is in a range of 62 Rockwells. So that is pretty typical for bearing assemblies like these. So the next thing I'm going to do is actually go down and mic every dimension on it, on the pin and in the bore, and basically build a table for myself to see how much clearance there is between the various components. You know, it's mainly just for the assembly, and based on that, that will be a great help for me to design my lifter or tappet. Okay, so I got my micrometer here. I always take out the battery, make sure that it will not leach anything into this device. So just turn it on. She's flashing, and we're gonna go inches and millimeters. Got 3 zeros. Put her in this 3D printed device to hold it properly, and I can start the measurement. So I'm going to start with this Ford Mustang. Okay, take the pin out, everything falls apart. It is 64 degrees in the workshop, just for the record, and I'm measuring that size 7641, and 90 degrees is 7641. So I'm going to make a note of that. Okay, so the Ford Mustang, the pin is 7.641. So that's the size of the pin, and I can move the pin back and forth, and it always shows 7641. It doesn't matter where I measure it. And that's what I was talking about. These are high precision parts. You cannot really make them at small quantities. So the next idea was to measure the bore, and I had this set. These are just telescoping gauges. The idea is that you take the gauge and then you stick the gauge in a hole and lock it in, but you can see this gauge doesn't really go in. So the smallest telescopic gauge didn't work. So what I ended up doing is bought myself a Tappet small hole gauge, and this is 0.3 to 0.4. So 0.3 would be 7.5 millimeters. So that's just about the right size. So the next thing I can do is introduce this into the hole and start tightening it up like that. And when it locks in, you basically get the size. And looks like it's a little larger, so it takes a little feeling of that size. And now I can measure across this, and it shows 7714. So the hole is 7714. So what I typically do is I create a mark on the parts. So for example, I create a plane this way and this way, and so I'm going to go in and measure that, okay, and get the size for that, making sure that it's in this plane, you know, measure it in the perpendicular plane, and then measure on the other side. So now I get 4 measurements and maybe use the average of that. What I've done in the past is measured a lot of size with the micrometers on a male part. So this pin would be a male part typically, and I measured the size, and then I was averaging it, and I always get like 2 maybe 3 microns of tolerance field, so plus minus 1.5 micron. And then when I was using the telescopic bore gauges, I typically get 15-20 microns of tolerance field. So I'm looking forward to use these small hole gauges and see how far they can take me, and how precisely I can measure parts with these. Well, 30 minutes later, the numbers are in. One day before the election, so that kind of tells you the story, how fast this worked tonight. So again, 64 degrees in a room, it's not 72, that would be ideal. There's 5 different designs, and here's the pin size, and then these are 4 measurements for the hole, and there's the average for the hole. And then this is the diametric difference. So on the Ford, in the case of the Ford, there's 59 microns clearance. A Great Wall 46. The Harley is 8. That kind of surprised me. The Hyundai is 74. And then this Racer M150 GY Racer is 20 microns. So this will be a great help for me on the design. Again, you cannot really learn everything from the books. You need to go take stuff apart and just basically make your hands dirty with it and understand how the parts stack up, because it's one thing to design something, it's another thing to manufacture it for mass production, and it most of the times changes the entire design when you design something for mass production. A couple other interesting things. In case of this Great Wall, I was measuring the size, and 2 of the dimensions came out 8.761, 763 on one side, and on the other side it was 993 and 9016, so way off, way off. And I think I found the problem with that when I was pressing out the pin. The pin is so hard and the aluminum is so soft. You can see that the pin completely scored the surface right there. So when I'm measuring it, I actually measured it scoring into it. And also most likely when I pressed the pin out, it increased the size. It acted like a mandrel. The other interesting thing is that the Harley only had 8 microns. That's a really precision fit. I actually have 3 more sets, so when I purchased this there were 4 in a set for like $10 or $15, so it's not really much. Just wanted to give this another chance and show it to you. What's inside. So all these parts came from it. So there's a little valve. This is just the plate that's inside. There's the roller, the pin, and the needles. And then inside here, I don't know if I'm going to be able to. So you can see there's 1 piston. Okay, so this is, I would actually call this a saddle. And this saddle has that hemispherical indentation where the push rod sits. You can see there's a hole, and from the shape and size I can tell you that this is metal, injection molded or powder metal component. Okay, so that's the saddle, and this is the interesting component. So that's a piston inside a piston. Okay, so this is a piston that moves up and down. There's another piston that moves within that piston relatively. So what we got here is we have this spring, and it's a relatively stiff spring. I would say it's 10, maybe 15 newtons per millimeter, the stiffness. And so that rests on the bottom of the lifter. You can also see the hole. Let me get a needle. Okay, so here's this hole on the side. That's where the oil from the gallery will get inside the lifter, and you can see that hole protrudes to the inside, so it will let the oil to able to go in. And so this is the internal. These are the internal parts, and I don't quite remember. I believe this part was down here, and it tacks some kind of a valve, and then this was on the top of that. So there's kind of a loose fit, and then down inside here, and there's a valve. Okay, so this is a one-way valve that you can see there's another gallery here. I didn't actually mapped it out exactly how it works, but I assume that the pressure is exerted on this side, and that will move this relative to the body, the tappet body, so it will kind of move out and compensate for the valve lash. But in certain cases, that oil, you need to evacuate that oil from underneath here. I think that's why there's this extra valve here. But it's this piece here, I think it's a press fit piece. Let me see if I can get it out. Okay, it's moving. So there you have it. So you can see there's a little valve, a little spring here. Okay, so that little spring is gonna pre-stress this plate, this little plate, and that little plate rests against this part here. So the oil from the inside can come through this one. So this basically acts as a valve. So here's some information and some footage about the press fit. I used my calibrated load cells that I calibrated with my weight to measure the press out force, and here's the press out force for one of the assemblies, for one of the pins. Again, this is not a frictional joint, it's more like an interlocking joint. So that's it for today. Hopefully you learned something and you enjoyed it a little bit. Thank you for your support, and if you like it, please give me a thumbs up, subscribe, and come back next time. Bye.